Hi and welcome to Introduction to Structured Programming. As always, we would ask for quick feedback. If you can hear us in the last row. Does it work? Yep, perfect. All right, today I'm here together with David, so happy to have you back also in the lecture. We'll also see you now also in the next lectures, so I'm really happy about that. And today we have reached a milestone, an important point maybe in the lecture, because today we will have a look at pointers, which is a crucial concept when we talk about the C programming languages. It's the foundation for many other concepts that we will have a look at in the lectures or in the upcoming lectures. But we will also take a look at strings. They are also very important, very useful. And before we start with pointers and strings, we will also have an organizational part. So we've already heard it in the practicals. Today we will hand out assignment 2. This will be done after this lecture. Again, there will be an announcement on Discord with all the important information. So, for example, how you can submit it or should submit it. And the deadline for assignment 2 is in approximately 3 weeks. It's on the 19th of November. It's Wednesday at 6 p.m. But you will find all of this information then in the announcement on Discord. Today we will also release further weekly exercises. So we will release 3 more weekly exercises that are related to assignment 2. Again, you can find them in Teach Center. And we want to highlight it once more. Please work on the weekly exercises, because if you don't do or do not pass more than 50% or at least 50% of the weekly exercises, you will get a deduction of 25% for assignment 2.
Yeah, it should be assignment 2. It's assignment 1 here, but it should be assignment 2, of course.
And the deadline for the weekly exercises is exactly the same as for the assignment 2. It's again Wednesday, 19th November at 6 p.m. All right, but before we start with pointers, with the exciting part of today's lecture, we will have a short recap what we did last week. And last week we introduced arrays, which are just a sequence of values of the same data type that we can store in just one variable. And for that we have prepared again a Slido quiz, so you can again join via scanning the QR code on the top left or visiting slido.com and entering the code. And in this first code snippet, you should guess the output for a given array containing 4 values, and we want to sum 2 values of this array and then print it. So you have several options from which you can choose one.
An easier one to start, maybe. The other 2 we prepared for the recap are a bit more challenging.
Okay, so last time we reached 100 responses, but let's see if we can reach it today as well.
Okay, last few seconds for you to decide, I would say. Let's wait until 80. Oh, yeah.
All right, let's reveal the answers here. And congrats, many of you, or most of you, got it right. So we just add two values here, numbers at index 1, which is 20, and numbers at index 3, which is 40. That's the case because we start counting with zeros. So this is the 0th element, so the numbers at position 0 at index 0, numbers at index 1, and so on. And that's why the result here is 60. Then let's come to the next quiz. Again, we have prepared a code snippet, but there's one statement missing. We've just seen it before in the practicals, how we can calculate the size of an array, because there's some tricky part when we want to calculate the size. We cannot just use, or maybe we can use the size of operator, but yeah, now it's your task to find the line that correctly calculates the size of the array and therefore prints size is 5. Okay, maybe we can reach 80 again. A few more seconds. And let's take a look at the answers. And yeah, again.
Great, okay.
Many of you got it right. So when we want to calculate the size of an array, we have to first take the size of the array variable. So we want to take the size of values in this case. And after that, we have to divide the size of values of the variable by the size of the first or any element of the values that are stored in the array. So we've seen it in the practicals. We could have used, for example, also size of values divided by size of double. So doesn't matter if we use the data type double or if we just use values at index 0 or any index actually. And why do we actually need this division? Because in this case, we have the variable double values, which is double, okay, we have 8 bytes. It requires 8 bytes in the memory. And we have, in this case, 5 values. So 5 times 8 is 40. So if we would just use, for example here, size of values, we would get the result 40 as the size. But this is not what we want. We want to know how many values are in the array. And that's why we have to divide this value 40 by the size of one value. So in this case, the size of one double value, which is 8 bytes. So 40 divided by 8 is then again 5. And this is how we know that the size of the array is actually 5. All right, and I think now this is a really tricky one.
Yeah, so that now checks if you really had a look at the practicals, and we have a 2D array here, and we iterate over that, and then we wanted to find the max score and then just print it out. Maybe we should give like, I don't know, 2 minutes for that because it's a bit more code here.
Yeah. So what the goal would be here is to find the maximum score of all values that are given in the two-dimensional array. So we iterate through the array, through the two-dimensional array, and we want to store the maximum score in a variable and at the end print the maximum score.
should we give a hint here?
Maybe.
So for everybody who decided very fast and just found out what's the biggest score in the double array, have a closer look. There's an error inside the code.
Yeah. Something that happens regularly, especially if you use
I and J as
variable names.
Yeah, variable names.
Can be very tricky to find these kind of bugs. So whenever possible or whenever you use I and J or just one character variable names, maybe you should change that and use variable names that are helpful also when debugging the code. Okay, let's wait a few more seconds, maybe again until 80, and then let's reveal the answer. Okay, I'm really curious. Let's take a look.
See. Oh, great. Didn't expect that.
No. I also didn't expect that. But why is this the case? Why do we get 88, but we have 90 here or 92 as the highest actual score?
So the problem here is the highest actual score is, great. The highest score is 92. But the problem is that we are taking the score I. So the row and the column is the same. It's not ij, what we want to have, because we are comparing for this. So the thing is, we are here in the second row. We want to have, so I is 2 here. We would want to have j, which is 1, because it's the highest one. But we access here score at row and column I, which means we are accessing this 88 here, and that's why 88 is the result.
So actually the iteration through the array is correct. So we correctly iterate through it. We could access every element in the two-dimensional array. But yeah, as you said, we are only considering the scores when we're using II, which is 1, 2, or 3. And that's why we only consider these values here, these 3 values. Everything else is skipped. We cannot access them when we just use II. And yeah, the maximum score of these 3 values is 88, and therefore this could.
If you would use, instead of I and j, row and column as variable name, would be more obvious, because then you see here pretty fast you access row, for example. That's a lot easier than I and j.
So please do not use I and j, as you said. For example, if you are having a two-dimensional array, row and column would definitely make sense to use as variable names.
All right.
Good.
Then let's move on with today's topics. And today we are, as you said before, we are diving a bit deeper into computer science. So until now, we've talked a lot about C and programming languages in general. So programming languages and concepts that are applicable for many other languages, loops, conditions, variables, arrays. I think nearly every programming language has these components. But today we get one step lower, so to speak, and we have a closer look inside the computer and inside the memory of the computer. So in C, we have the possibility to really access addresses in the memory. Many languages do not have these possibilities, but in C we have that. So let's see what C has for us to offer. Before that, I need a bit of a background knowledge. Maybe most of you or many of you already know this, but just as a recap, we have different kind of representation when we talk about information. I think all of you know now the binary representation, where you have just two symbols, you have 0 and you have 1. I think all of you also know the decimal representation, where you have the values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you start with, again, 1, 0, which we speak to 10. Yeah? And maybe also a few of you know the hexadecimal representation, which goes just a bit further, which is from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But instead of 10, we move on to A, B, C, D, E, F. F relates to 15. And then we start again from the beginning, like we do in decimal, where we have then 2 digits from 1, 0, and we speak with 10. Then we continue with 1, 0. So that's important information, because the memory is by design, or let's say everybody does it like that, always addressed with hexadecimal values. So this is an example of a grid. Let's say this is our memory. And you can see here that here are my memory addresses. I have the memory address 0, 1, 2, 3, 4, 5. That's very common to us. Then instead of 10, where we would have had 10, we say that's the memory address A, because we count in hexadecimal. A, B, C, D, E, F. F relates to 15 in decimal. And then, as I said before, 16 again is 1, 0. But that's a problem, because 1, 0, you don't know by, if you have a look at just this memory address here, you don't know that it's a hexadecimal value. Could also be, of course, a decimal value.
Or even a binary value. So.
Or even a binary value, yeah. So what you usually do, and this is also everyone in the computer science world, let's say, when you use hexadecimal values, you always write this 0x in front of the hexadecimal values, and then you know instantly, okay, this 1, 0 here means it's a hexadecimal value. This is not really a value that adds to this value here. It's just a representation that you know that everything after this x is a hexadecimal value. That's it. And you will see a lot of these hexadecimal representations in our slides and also in the other courses and so on. But this is just like a bit of a background knowledge. It's just a number. You can represent it as decimal. You can represent it as binary, as we have seen in the practicals today. Or you can also represent a number as hexadecimal. The big advantage of hexadecimal is you have more symbols. So higher numbers and very, very large numbers don't need that many places. Yeah? So with binary, it can get very, very large. Decimal is a bit easier then, and hexadecimal, it's again a smaller number to write. Usually, we have very, very large memories. So we have, let's say, 8, 16, or 32 gigabytes. So there are a lot of memory addresses inside such a memory, and that's why we use this hexadecimal representation. Okay. Addresses in memory. We can find out where a variable is stored. So you know that one. You know that I have my variable here. I give it a value, and then I just print it out. Very common. Let's say this is now our memory on our computer. And on this line, we have stored our value. In this case, I'll show it as a binary representation. But if we would use the binary converter we have seen from the practicals today, you will came to the conclusion that the variable as decimal representation is 42. So that's why the output here is also 42 in this case. So the computer puts my variable somewhere on the memory, in this case at this memory location here, but we don't have control over that, where it is stored. That's what the programming language does for us, but it somewhere stores my variable and then I can access that. But what if we want to know the address of this variable? So we want to know where is it stored. And here you can write it like this. So again, my variable 32, and then you can use this ampersand, or in German, I think it's kaufmännisches und. So the and symbol. And if you write it like this, it gives you the address of a variable. And if you write here person P, P means, in this case, pointer. So we are coming now closer to pointers. It shows you the address, and the output is something like this. Of course, this is just an idea. Yeah, this is or let's say this is an output which can happen.
Could,
yeah, but we don't know the exact number. But this is a possible output if you run this code. Okay, so we now know that we can have access to the address. We can also print it, but can we store it somewhere?
That's a very good question, actually. And yes, we can do it. We will now take some time how we can do it, so to explain how we can do it, how this is done internally, and this is now when we talk about pointers.
Yeah.
Pointers are extremely important. So once you can understand what happens under the hood, you are very well prepared, I would say, also for the upcoming lectures and also for upcoming courses. And please immediately ask if you have any questions, if you do not understand something fully, because we will need pointers next week, the week after that.
From now on in every lecture, and
Yeah.
I think you will need it in every programming lecture in the next semesters. So we will take our time now. It's very good choice that you are here today because you can ask questions. This is maybe the most important lecture.
Probably, yes. Yeah.
I think most of you have heard about these pointers, which are very hard to understand. It was also hard to understand for us in the beginning, we have to admit. That's why we dedicated this whole lecture just for pointer. And again, also the next lecture is also about pointers. So a lot of pointers in the next hours. Okay, but let's start. What are pointers now?
Let's start with the exciting but also tricky part. First of all, a pointer is just a variable. So you've seen different variables, they can have different data types, and every variable can store some kind of value. We have mostly used integer values or characters, double, float, whatever. And a pointer is just, another variable that can store a value, which in this case is an address. So the value that is stored in the pointer variable is an address, as we've seen before. This large hexadecimal number can be any large hexadecimal number, can be any address. And when we want to create a pointer variable, we use a special operator. It's the dereference operator, so not to be confused with the multiply operator.
Yeah.
So whenever you want to create a pointer variable, you have to use this dereference operator as shown here in this declaration and initialization of the pointer variable. So this is a common variable that we have used already many times. It's just a variable of data type integer that stores the value 42. And we've just heard before, every variable is, or the value of the variables is somewhere stored in the memory. So for example, here we have this variable, my variable, with the value 42, and this is stored in the memory at the address location 0x7 and so on. Any address. And now we just create another variable here. But we use this dereference operator, which indicates that this variable is a pointer, and therefore it will store an address of, for example, another variable. It just stores an address. So whenever we want to declare a pointer variable, we have to use this dereference operator. And same as for the variable, my variable here, this variable here also is somewhere in the memory, so it has some value. In this case, the value is not 42 anymore, or any value that we just use for initializing it. But in this case, the value is the address of where my variable is stored. So we've just seen it before when printing it, for example, when printing the address of a variable, we use this ampersand, so the address of operator, and once we use this, we assign the address as a value to this pointer variable. And yeah, the pointer variable again is somewhere in the memory. It again has some address, could be something similar as shown here. But the important point is that the value of the pointer variable shows, or points actually, to the location of, in this case, my variable. So this is...
That's basically it.
That's basically it.
That's pointers. Yeah.
That's what pointers
it's
do.
It's just an address to another location in the memory. But of course, there are some pitfalls, and it will be a bit more challenging in the next few slides. But that's the basic concept. Any questions to this basic concept? Yes.
If my pointer points to, in this case, an integer variable, is it necessary that the pointer is also in with the dereference operator?
That's very, so just to repeat the question. So we have an integer variable here, and the question now is, does the pointer variable has to have the same data type as a pointer as well? So that's the question, yes. Right? That's a very good question, and already a bit advanced, I would say. So
let's say for now, yes. There are ways to where I could say it's not necessary, yeah, but for our knowledge now, yes. It should be the same data type, yeah. So if my variable would be a double, it should be a double pointer then. Yeah.
We will come to that, I think, in 2 weeks.
Yeah.
So, if possible, always try to use the same data type because it improves readability, maintainability. But as you said, no, not necessarily. But the more advanced answer will come in 2 weeks then. Okay. Any other questions? Yes.
So the question is, if we have a two or multiple, we will come to that. Yeah, that's again also an advanced one. We will come to that where we have pointers then. Yeah.
But it's possible, so you can do this.
Maybe let's move on to printing the basic or printing these pointers. Yeah. So we have seen that before. We can print the address, but we could also print the pointer we have created before.
And we don't need the address of operator anymore, so we can just use this variable pointer here. So if you compare it with this printf here, we need to use the address of operator, the ampersand, but we don't have to use this anymore here because we have already defined this as a pointer, and therefore we can just use the variable without requiring the address that we want to print. Of course, we will come to that again in a few minutes, but we don't need to use the address of operator here because we want to have the value of this variable here. So we want to have the address of my variable.
Yeah. So that's basically this step. What printf does, it points to from the name to the value.
But what if we want to print the address of the pointer? So if we want to print this one here.
Yeah. Any ideas how we could do that? How we can access this address here? So the address of the pointer. Yeah, I think you were first. A point to the pointer. Yeah, how do we get to the address of the pointer? With the ampersand again. Yeah.
Exactly. So if you want to print the address of our pointer, so not the value anymore, which is again an address, but the address of another variable, we can just use the ampersand, the address of operator, and this will then print the output, or as an output, the address of our pointer. So where our pointer is stored in the memory.
Can I do this once again and have then store this address into another variable?
Yeah, that's a good question. So it's related to your question just before. Of course, we can do that. We can create another pointer variable that it points to our first pointer, print this address again, and so on.
So you can create kind of a chain?
We could create. Yeah. I don't know if it makes sense all the time, but there might be some cases where you should do this.
But for now, let's stick to usual pointers.
Okay, so it's cool that we have now stored the address of a variable, so we can have the address as our value when we're a pointer, but usually we want to get to the value of the actual variable. So we know the address, but we don't know the value of this variable, where we know the address yet. And so we want to go this step here. We want to go from the value of the pointer to the address, and then we want to do something with the value of my variable. And for this, we again use the dereference operator. So this is actually not the same. So here we define, or we declare and initialize the pointer variable using the dereference operator. But whenever we are not declaring a pointer and we use the dereference operator, we want to get the value of this, or of the variable, with the address, for example, stored here.
So basically we are going this way.
Yeah. And dereferencing a pointer, as shown here on the slide, is what we need many times. So that's the basic use case of pointers, that we want to get the value of a variable where we know the address, but not the value itself.
It seems a bit odd because I also have access to my variable. Why would I access the variable or the value 32 over this pointer when I have access to my variable?
That's a basic question about why do we need pointers at all.
Yeah, and we will see a few cases today where we would need pointers actually, because otherwise it's not possible to solve it without pointers.
Yeah. Are there any questions to dereferencing a pointer? Yes.
Why is the reference operator used to initialize and to point to whatever address exists? Like, if we say that as this name there exists an address, but for some reason, but that's, again, I don't understand why initializing
So the question is why, and I can totally relate to you, why is this one here, so this asterisk here and this one, the same symbol, but does different things? That's very confusing. And I also hated the people who invented this because, yeah, it makes us a lot of headache. But think of if you have a data type here, it's always a declaration. And here in this line, you just say, I'm creating a pointer here. This just means I'm creating a pointer, which means the value is, the value is an address. And if you don't have a data type here at the variable name, because we already have this variable declared, then the same symbol, unfortunately, means dereferencing. I cannot give you an explanation why they did it.
I also agree. It's confusing.
Yeah.
But yeah, as you said, David, whenever you have a data type, when you declare a variable, you know this is used to declare a pointer variable. And if there's no data type at all, we know, okay, this is used for dereferencing.
So dereferencing an existing variable and declaring a non-existing pointer. That's the difference. Unfortunately, with the same symbol,
Yeah, there's another question.
Would you run into trouble if you were to try to get the value from one pointer with the dereference operator and then try to multiply that with something else so you get this star symbol multiple times? Do you have to use brackets to define the order in which you want to do it?
Yeah, we have another confusion, of course, with the multiply symbol. You're totally correct. Do we talk about that in future? I don't know.
We have talked about operator precedence last week. So I would recommend, this won't be an exam question, for example, so you will definitely get the table for operator precedence during the exam for that.
So which means which operator counts first, yeah? So what operation is done first is dereferencing before multiplying, for example. But I would always recommend to use parentheses for that, because it's just for readability.
Yeah, and there you're 100% sure
Yeah.
what's going on.
One more question, yeah. Yeah. So you mean this value here. This value is the address of my variable. So it's just the location of the variable, my variable, somewhere in the memory. And with this address of operator, I will get this address, store it here into this pointer, and then go this way to have a look where my variable is stored and can access now the value there.
Yeah. So the value of this variable is the same as the address of, in this case, my variable. And the reason for that is because we store the address of my variable as the value to the pointer. So this has to be the same. Otherwise, we, for example, couldn't reach the value anymore, so the value of 42 anymore by just using the pointer variable. Okay. Any other questions before we continue?
There's one more question.
Yes.
Okay, so the question is, what if we point to the value? That's not possible, that's not a pointer. Because pointers always point, or the content of a pointer is always an address, or a hexadecimal representation, just a number in hexadecimal representation, and it hopefully points to an address of another variable, where then a value is stored. If you have here, let's say, I don't know, a value of 50, then the program would interpret this value 50 as a memory location maybe would go to this memory location 50 and see what's stored there. Obviously not your variable, and you will have so-called segmentation faults or wrong memory access, but we will come to that also.
So, of course, in theory, you could store any value in a pointer variable.
Yeah.
But as you said, you most likely won't be able to then, for example, dereference this address and get the actual value of that, because I would say most of the addresses in this program, for example, here, you just cannot access them.
And if you overwrite this value here or change the value, then you lose the connection, and then you can not access anymore the value 42 because you lose the connection, you lose the address where it is stored. I think we have a quiz now.
Yeah.
Let's see what you think about that. So we have a value, once again, an integer with initialize it with 5. Then we take the address of this value and store it into an integer pointer. Then there is one line missing.
And we want to change the value from 5 to 6.
Yeah. So which of these lines can change the value to 6?
So there could be multiple statements that lead to the value 6 of the variable value. Okay, now it's working again. We're again having some troubles with the connection. Okay, let's wait again for 80. And
All right. Ah, cool. Very nice. So the first one is a bit obvious.
yeah.
We can, of course, even when we created a pointer, we can also access the original value variable here. So value plus plus works because it just increments the value of value by 1.
So yeah, this variable exists independently of the pointer variable that we have. So we can modify it, can do whatever we want.
Second one is more interesting.
Yeah, especially the second and third one.
Yeah.
So I think this also relates to the question just before. Because again, here we, as you said, should definitely use parentheses to make clear that we first want to dereference the pointer so that we get the value of the address that this pointer is pointing to, which is in this case 5. And once we have the value, we can do, in this case, just a postfix increment and therefore can increase the value to 6. So we first have to dereference it. After that, we can increase the value.
But why is the third one not correct? Because it's basically the same.
Yeah, that's tricky. But again, we have to think about operator precedence. So if we first increase, in this case, value pointer, so if we want to increase the value and dereference it after that, but if we change the value of value pointer, so the address that is stored as a value, we are pointing to a memory address that we most likely do not have access to. We are not allowed to access this memory location, and therefore we are also not allowed to dereference.
So in this case, this value plus plus is executed first, and then the dereferencing is executed. Because we are missing the parentheses, and there is this kind of strict rules which operators are executed first. And this plus plus, so this increment is always executed before this dereferencing. And that's why we need this parenthesis to have or to reach what we want to do here.
Okay.
The other ones are the address of value plus plus is again a problem with operators value pointer plus plus would also increase the pointer, so the address. We are not modifying the actual value 5, we are modifying the address that's stored in value pointer, and the other ones are also wrong. Yeah,
but it's maybe interesting. Here we want to dereference a non-pointer variable. So we have the variable value, which is just of the data type int, and we want to dereference it, and this hopefully doesn't work. So you cannot dereference just, for example, an integer variable. So you always have to dereference a pointer variable.
Yeah.
There's one question, yeah. So if, okay, maybe I repeat the question if I got it right. The postfix increment is if we use the ampersand executed first or if it's not. Independently, if it's executed first or not, why would we want to print the address of value? Or I'm sorry, I didn't get. Yeah, but if we take a look at the operator precedence, no, I think you're right. So the postfix increment is actually executed before the address of operator.
I think so too. Yeah,
Yeah.
not sure, but yeah, I think so too. But it's again not correct because we get the address of the variable value and increment then this address, which makes no sense. But you're correct, yeah.
Yeah. Okay. Let's continue.
Yeah, let's move on because we already used this ampersand.
We've used it, I think you've mentioned in the very first lecture when we talked about scanf. So I assume you have already used scanf. It's just one function that is provided in the standard IO header. And whenever we use scanf, we have to pass not just the variable value, but we have to pass the address of value. So scanf requires an address and not an actual value of a variable. Because if we would just store value without the address of operator, it would just pass 0 as a value to scanf. And what should scanf do with the other value 0? So we want to pass the address of value so that scanf can actually store it in this memory location that we pass. So essentially scanf just takes a pointer, so we need to use the address of operator, or we can also create a pointer variable here and then pass this pointer variable without using the address of operator because we already store the address of a variable here in this line. And if we now pass this pointer variable, scanf receives an address and then stores the value at this specific address.
And that's the first use case for pointers. So I hand over the address to a function and say, store there whatever you want. at this location, and then I have accesses because it's basically my variable outside of this function, and you can store at this memory location whatever you want, for example, the user input. Yeah, so it gives you control, or it offers you the possibility to hand over control to others, but still have access to the memory location or to the variables, in this case, the value here.
Yeah. So we are basically sharing the location of where the integer variable value is in the memory. We just pass it to scanf. Okay, scanf can do whatever it wants. So it has the address, it can modify the value, and we then again use the either value or value pointer when we want to do something, when we want to print or access this value.
Okay, and yeah, where to put it? If I think that's a philosophy question.
Yeah, definitely.
I like the left one because, in my opinion, the pointer belongs to the data type. Yeah, but there are also advantages of the right version. You can put it wherever you want. It makes no difference for the declaration. The compiler accepts both. But please be consistent over your program, because otherwise it's again confusing.
Yes. So as you said, there are pros and cons for both versions. If you put the asterisk next to the data type, or if you put the asterisk next to the variable name. For the second use case, or for the second approach, there are some use cases where it might be beneficial, but yeah, essentially it doesn't make any difference because the white space is removed, and so for the compiler, there's no difference if we put it next to the data type or to the variable name.
Okay, so I think we have to move on a bit because we are already used a lot of time for the pointers. It is worth, but yeah, let's move on.
Okay, so we've seen already many data types. We've seen characters, int, long, double, float, and so on. And now we also have a, let's say, new data type, which are pointers. And we want to find out what is the size of such a pointer. So if we have this code snippet here, we want to just print the size of a character pointer, an integer pointer, and a double pointer. And yeah, maybe due to the time, we will just reveal the answer here. And maybe it's a bit surprising that the size of all of these pointers is actually 8. So we assume it's on a 64-bit system. We will assume it for the rest of the lecture. There's a difference if we have a 32-bit environment or a 64-bit environment. So on a 32-bit environment, it's just 4 bytes. On a 64-bit system, it's 8 bytes. But the important point here is that every pointer, independently if we have a, or doesn't make a difference if we have a character pointer or an integer pointer or a double pointer, it's always 8. So whenever we have a pointer, we know, okay, it's 8 bytes.
Why? Because it always stores an address, and addresses are just always 8 bytes.
On a 64-bit.
Doesn't matter if this address points to an integer, to a character, or whatever. It stores the address, and an address is always 8 bytes long.
And this already brings us now how addresses and functions are related. And here we want to start with an example that we have already seen in lecture 3 weeks ago or 2 weeks ago in the lecture where we talked about functions. And here we wanted to swap two numbers. So we have the numbers 5 and 6 stored in two variables, and we have a function that swaps these two numbers. But we have seen, okay, this is not exactly what we want. It doesn't actually swap the two numbers. The two numbers stay the same. Why is this the case? Because we only pass the value of x and y to this function here. Here in this function, the parameters just receive a copy of the value. So just have the values 5 and 6. We swap them here, but this doesn't affect the variables x and y here. So these remain the same. And now we can also take a look at void. We have already talked about it briefly, and we know that void means nothing, so nothing is returned. We don't need a return statement. We can just leave it as it is. Or it can be arbitrary, so it can be beliebiges. We will especially take a look at this next week
time.
then,
Yeah.
but it's maybe important again to just know that void can be nothing or actually anything.
Again, the
Better
same word, two meanings. Yeah,
Yeah.
not happy with that, but yeah.
We will take a look at this. And if we now again take a look at exactly what happens here in this example, in this swap example, we have two variables here in the stack of the main function with 5 and 6, and we have three variables in the stack of swap. Again, we have x and y, and we have temp, and in the stack of the swap function, it's swapped correctly, so this is what we actually want to have, but we can see in the stack of main, this is not what we expect when we have the swap function.
You can also see they have different addresses, which means they have different locations in the memory. So this main here, this x and y here, have this address, and the variables inside this function have this address. So they're not the same, even though they have the same name. They have different locations. So if I modify one memory location of x here in this function, I do not modify the x in the other function.
But yeah, we've learned about pointers. We've learned about pointers that can store addresses as values, and maybe we can use pointers now to solve this problem and to swap two numbers using a function correctly. So
yeah, don't be confused about this. All these stars you are seeing now, it will make sense.
But again, we just have one variable here, x and y. So these are the two numbers that we want to swap. Again, we have addresses, in this case 4 and 8. And we now pass not the value anymore. So we don't pass x, which means 5, but we pass the address of x. And we pass the address of y. And now that we have passed the address of these two, or the addresses of these two variables, we cannot expect an integer variable anymore as parameters in the swap function, but we have to expect integer pointer variables. So we have to now define an integer pointer for x and an integer pointer for y, because we pass the addresses of x and y to the function. And now, what you have mentioned just before, we can now see, okay, x is stored in the memory at address location 0x4. And now we see, okay, the value of x is not 5 anymore, but it is 0x4. So we now store the address of x in this variable here. The same for the variable y. So y is stored at, or the value of y is stored at the memory address location 0x8. And in this variable here, in the integer pointer y, we store the value of the address, which is 0x8. And now that we know that we have the addresses of the original variables, so that were passed to the swap function, we now can work with them, we can dereference them, and by dereferencing, we just go this way here from 0x4, this way all the way to x, which is, when we pass it, still 5.
Yeah, so when we go back, and we are here in the code, x is 5, y is 6, and when we are here in the code, the actual values of x and y in the main function are swapped because we access them through the addresses, through the pointers. And as you said before, we have again here a lot of stars, I know. We are declaring the 2 pointers, so the 2 variables that hold an address to an integer, x and y. And here we are dereferencing the x value, so going, as you said, going this way down here to access this value. And you have to dereference the x, the y, and you store this temporary variable in a usual integer. So now you have swapped x and y using pointers.
And now we have already achieved the result that we've wanted. So we have actually swapped the 2 values, x and y, using the swap function by using pointers. So by passing the addresses of the variables and dereferencing these variables here, so accessing the actual memory address location and the values of these variables, and by just simply swapping them.
And this concept has a name. So in the right side, you see the new version we just learned, and this is called call by reference, because we are calling the swap function with references. Reference is this address of operator of x and address of operator y. This means it's a reference to another variable, and that's why it's called call by reference. In contrast to that, when we just hand over the value, so the value gets copied, it's call by value. That's the huge difference here. And you will learn that at some point when you create a function, you have to make a decision. Do I hand over my parameters by value or by reference? So these are the 2 possibilities. So do I make a copy of it by value, or do I want to actually modify the same variable again? Then I use reference.
And this concept is not only related to the C programming language, but there are many other programming languages where you have to take care if you pass the value or if you pass the reference. So there might be some behavior that is not desired. For example, Java, I think also in Python, it's possible, where you can pass it either by value or reference. And now you know, okay, what happens under the hood, that you actually pass the memory address of one variable if you use, for example, call by reference. And what's important here is that you, if you use the call by reference concept, that you have these pointers here as parameters in contrast to the integer variables here if you use call by value. And whenever you want to access the actual value of x and y, you have to dereference them to get the values of x and y. Okay. Are there any questions?
Yes.
Yes.
So what's the advantage of call by reference in contrast to call by value? So as you can see here, the left version does not work because the left version does not swap x and y. It just creates a copy of it, but it actually does not work. As you can see, x is still 5 and y is still 6. So the original value is here. On the right side, the swap has worked. So whenever you want to hand over some data to another function, let them do something with it, and then I want to have, I want to work on my data, and I want to later on use this calculation. It was what was made, for example. Then I need references. So we've seen it before with scanf. I hand over scanf an address. It writes there whatever the user puts in, and then I can work with that. If I use call by value with scanf, I just give scanf a value. They store the input somewhere, and I have no access where scanf puts this value.
So especially when you think about scanf, you can pass multiple addresses. So you cannot only return one value or address that was entered by the user or whatever. So also in this case, in the swap example here, you want to modify two values or even more values when you have another example. And you cannot do that anymore by just using a return value, because you want to have two values that are actually returned or calculated in this case. So for example, whenever this is the case, you should definitely use call by reference.
And a lot of functions we are introducing you in the next few hours actually require you to hand over an address. So they require a pointer as a parameter because they do something with the data you hand over to them, and then you can work with them again. Yeah. So I will give you a memory. You can do whatever I want. And when you're finished, I can have a look at this memory again.
And I can do whatever I want. So, okay. Any other questions?
Okay. So, one more quiz for you.
Okay, it's quite similar to the swap example. We have two variables, integer variables, and we, in this case, pass one by reference. We pass x by reference and y by value. And now what is the output of this code snippet? Okay, we will wait a few more seconds. And let's see what you voted for. And congrats, many of you got it right. X is 5, Y is 3, because we pass X by reference. So we modify the value of X here by dereferencing A and doing some operations with P. But we pass Y by value, so we just pass the value 3 in this case, 3 stored in B, and we modify B in this case, but this does not affect the value of Y in the main function. So we only modify the value of X in the main function, but not Y, and yeah, this is the reason why X is modified. X is now 5, but Y still remains 3.
Okay, move on to arrays again.
We have briefly talked about them today in the recap. They're just a sequence of values which can be stored in one variable. That's basically an array. And since we now know something about addresses and pointers, we want to mention something that's very important whenever you use arrays together with functions. And that might be the case often. So whenever you declare and initialize an array here, and you want to print, for example, the size of this array, you will get the number of elements multiplied by the size of the data type.
So it should be 5 elements times 4, because we have integers, it should be 20.
Should be 20.
Yeah.
It is 20. But if we now have a look at the print size function, which prints the size again of this array, we see, okay, this is 8. Why is it in this case 20? Why is it 8 if we just print it in another function? So we pass the array to another function and print the size again. That's strange.
Yeah.
That's
very strange, because it's again, here in the print size, it's again an array. Size of numbers. What's the problem here?
What happens here is whenever we pass an array to a function, we pass this array, or this array is interpreted as a pointer. In this case, an integer pointer. So the size here, we already know this, it's number of elements times the size of the data type. But in this case, it's not the same anymore. It's the size of an integer pointer, which we know is 8 bytes. So it's a different interpretation of this array here and this array that is pointed, that is passed to this function. So whenever we pass an array as an argument to another function, this array is interpreted in this function as a pointer. So that's very, very important to know. For example, when you want to actually calculate the size of an array, you cannot do it like this anymore.
But that means that an array and a pointer is pretty similar, right?
It's quite similar, yeah. So
actually, arrays can be represented as pointers.
Yeah.
Or let's say an array is just a pointer to the first element of the array itself. But we will talk about that next week.
Next week, yeah. And now we come to a case that you should definitely remember, because if you do this, you will run into problems, into troubles. And this is the case when we want, or we declare a variable inside of another function, and we want to return this array to, for example, the main function. So we declare this variable here int array, and we want to initialize it by calling the function createArray with the length 5. Okay, we declare it here, we initialize all the values, and then we return this array. Looks good in theory at least, but you should never do that. Never ever do that. Not in the practicals. Never when you use the
You can try it out if you want, yeah. The computer will not break.
No.
But the computer will say, you're not allowed to do that.
Yeah.
Why not?
Why is this the case? We have briefly talked about the stack today already. We've also heard it in the practicals. But when we declare this variable array here, this variable only exists while the function createArray exists. So it's only in the scope within this function here. And as soon as this function ends, so when all the statements of the function are executed, this function does not exist anymore, and therefore also the local variables do not exist anymore. So when we now return this array here, and the address of the array is stored in this pointer variable, we would access a memory location that doesn't exist anymore, because all the variables of the createArray function do not exist anymore in the memory. We would try to access a memory location that we are not allowed to access, because this is not related to our code or our program anymore. And this then leads to, as you've mentioned, a segmentation fault. So you will just, it will crash the program.
Yeah. So the computer recognizes you are accessing memory that does not belong anymore to your program. So it says you are not allowed to do that, and it crashes your program.
So yeah, never create or then return a local array variable from one function to the main function or any other function. So you will run into a segmentation fault, and that's definitely not what you want your program to do.
Okay, let's move on to the last topic for today, which are strings. And string is basically pretty easy, let's say, because we already talked about arrays. But let's motivate this again with our memory here. Let's say this is our memory in our computer. We have some values stored at different locations. And let's see what's especially this data here in this memory location looks a bit odd. 72, 101, yeah, and so on. I don't know what this could mean. But if we have the ASCII table we can now say, okay, so this 72 is an H, this is an E, this is an L, this is an L, 111 is an O, and 0 is just 0. So we have stored here a string in this memory location, just hello.
Which is actually just a concatenation of single characters.
Exactly. So a string is just a concatenation, as you said, of single characters, and we can combine them. So strings are character arrays. So array is just a combination of values. In this case, a string is a combination of characters. But it needs always an and the and is defined by the null byte, which is just the value null. It's not the ASCII value 0, which is, when we have a look at this table here, would be 48. It's really this value 0, which is like translated to null. That's a difference. We will come to that and we'll see that often now. But it stops, or the string ends where this null byte is stored. So we need one more byte to store this value. So we have for each character 1 byte. The character needs 1 byte. And then we need 1 additional byte for the null byte. So how can we write this now in C? Like an array, we can write here character and then my variable name, create an array with 6, with the size of 6. And then I can write it like this, hello inside. And I print it with this %s, which means string. I could also omit this 6 here and just write character, hello string, and omit this here because the program will now know, okay, it counts from 1, 2, 3, 4, 5, and it knows that there is, again, also this null byte at the end, so it creates the array in the appropriate size for us.
And there's also a format specifier that we haven't seen before. So %s means that we want to, or the data type of the variable that we want to print is of type string or just a character array.
And what we also could do is, we could also write it like this. So create a char pointer, hello string, and this would also create for us an array and puts in the string hello, and all of the 3 versions automatically add the null byte at the end. So this would also work. This now leads us to the conclusion that arrays are very, very similar to pointers, because we could also use pointers to create these character arrays. We will see next week what are the differences. So there are a few differences, but in general, they are very, very similar. Okay, so now we know strings. Let's say we want to compare 2 strings. We have here 2 strings, str1 and str2, both with the same content, hello. So I think we could just write if str1 is equal to str2, print equal, and else print oh no. When we execute that, we unfortunately get oh no.
But it's the same word actually.
It's the same
hello.
content. Yeah, so sure. It should go through. H is equal to H, E is equal to E, and so on. So that's the same. That's odd. What actually happens under the hood is it does not compare your strings, so not the content, not the characters. It just compares the pointers. So the addresses where these 2 strings are stored. And if I print these 2 pointers, so the addresses where the strings are stored out, you can see that there is a slight difference, especially here at the end. They are on different memory locations. So when let's say this is again our memory, we have here 1 hello and we have here 1 hello. And we are comparing the pointers to the addresses, and that's why when we execute it like this if here is wrong, So we end up in the else branch. But how could we compare now strings? There is a library dedicated for string operations, so you don't have to implement it all on your own, which you can include. So you can write here include string.h, and this includes a string compare function for you. So you can write str compare and hand over the two strings, str1 and str2. Okay, we end up again with oh no, it's still wrong. What did we do wrong here?
I would assume that it would return true, for example, or 1.
Yeah, it should return true, but it does not. Let's have a look at the manual, and it says str compare returns an integer indicating this result of the comparison as follows: 0 if S1 and S2 are equal, a negative value if S1, so the first argument, is less than S2, the second argument, and a positive value if S1 is greater than S2. So it means str compare returns 0 if they're equal, so we have to write it here. Str compare is equal to 0, then it's equal, and now it works. That's, yeah, a bit unintuitive.
Yeah.
In my opinion,
common pitfall if you use string compare for the first time, or if you just start using the string h header. But once you're into that, once you know, okay, string compare returns 0, if it's the same, if the two strings are equal, then it's no problem anymore.
But remember, str compare uses 0 to be true, which is a bit odd. Yeah. This string.h library offers many other functions. For example, str length, which gives you the length of a string. And as you can see, I've handed here all of the declarations of the functions you can use. So str length, and you hand over a pointer or an array or an array of characters, so a string. It's the same in this case, and it will give you back the number of characters inside the string. Str length, I think, does not include the null byte, so you have to consider that. Str cut concatenates two strings together, so you have a destination and a source, and it concatenates the source to the destination.
So what's important for all these functions is that you take a close look what is the first parameter that is expected, if it's the destination, if it's the source, and what's the second and optional other parameters. So to take a close look, if you want to, for example, also for string copy, if you want to store the first string in the second string or otherwise. So it's important to take a close look what is expected as the first parameter and the second and any other parameters.
Yeah, so as you say, there's a string copy, which copies a string from source to destination. Str encopy is a bit of a modification. You have one more parameter here, n, so you can say, I just want to copy n characters, not all of them, just copy n characters. What is this size t here?
We'll come to that next week, maybe?
Yeah, it's basically very similar to an integer. It's just a number, just another definition of a number. So you can hand over here, for example, 5, and it will copy the first 5 characters. Okay, should we move on? What's the time?
I think it's already...
I think with that we close for today.
Yeah,
and we will continue next week.
Yeah, and it's totally fine to be a bit confused today, so that's absolutely normal.
Yeah.
If you have any questions, just let us know. We can also discuss them next time in the lecture. And other than that, thanks for being here. I hope it was not too confusing.
And we will repeat all of the pointer stuff next week once again. So yeah, thank you for being here, and see you next week.
See you.